Physics and Astronomy. Ooh, it's a little slight echo. Dr. Voit is an astronomy professor at MSU. His journey started in suburban Philadelphia. He graduated from Cheltenham High School in 1979 and from Princeton in 1983 with a BA in Astrophysics and Sciences. His Ph.D. in Astrophysics is from the University of Colorado. After completing his Ph.D., Dr. Voit spent 3 years as a research fellow at Caltech, 2 more as a Hubble Fellow at Johns Hopkins, and 8 as an astronomer at the Space Telescope Science Institute, working on the Hubble Telescope project, and afterwards joining MSU in 2003. Please welcome me in joining Dr. Voit.
Should I say anything about the first slide here? Well, here's my first slide for the talk, and the title is Colossal Black Hole Eruptions. It's supposed to be lurid and inspire your imagination. One of the reasons I like to give this particular public talk is even if you don't grasp all the science, it has some of the greatest imagery that I like to show. This is a galaxy. The yellow blob at the center is a galaxy known as Hercules A. And the pink is showing radio wave observations of 2 streams of matter shooting out from the center at nearly the speed of light. And it's energy from the black hole that's driving those things out. The other things you see around are other galaxies in that part of the sky. So this is what the talk's about. There are also some themes. We'll learn a little about what's out there in space, how it got there, and maybe a little bit about how we got here. So first, I want to familiarize you with what a galaxy is like. You've probably seen it, but you need to go somewhere dark these days. A couple decades, several decades back, it was a little easier to pick out the city lights. This particular photograph is above the fireplace at my home. It's not one of mine. It was taken by a very experienced astrophotographer on one of the islands of Hawaii. And what you're seeing in the center is that band of light called the Milky Way. And if you look closely, there's also some dark spots in that band of light. And many of you probably know we are a star inside the Milky Way galaxy. It's like a disk of stars. And when we're in that disk, when we're looking through it, it looks like a streak. We don't get to see the outside perspective, what the galaxy looks like, but this is what we see. This particular image is a map of the whole sky. It was made by taking pictures in all directions and stitching them together. And when you're looking at it, what I invite you to imagine is like a world map. If you had the skin of a globe and peeled it off and spread it out flat, you could see everything that was on the globe. If we had wallpaper of the whole sky, kind of the inside of the globe, and stripped it off and flattened it out, we'd see everything that's in the sky. So this is the whole sky seen as an oval projection. What you're looking at in the very center, that's toward the center of our Milky Way galaxy. And above the center, that's above the galaxy. Below, it's below. And this streak across the middle is what the galaxy looks like in visible light, if you could see the whole thing at once. Okay, so I wanted to orient you to that picture because you're going to see a few more pictures of this kind. This will be in the slides if you want to check later. This is a projected map of the constellations. And if I can pull out my pointer here for a second, people online won't be able to see what I'm pointing at. But constellations like Orion, oops, where's my light? Yeah, you can't, it doesn't reflect on this. But Orion is over on this side, and Sagittarius is right toward the center of the Milky Way. So if you can find the constellation Sagittarius in the sky, you're looking right toward the center of the Milky Way. To go back to the visible light map. Now, the dark patches are gas clouds that are in the Milky Way. They have particles in them. They're kind of like smoke. Astronomers call it dust. And it obscures our view, but if you use an infrared telescope, you can see through a lot of that. And we'll go to an infrared light image, and you get a better picture of what the galaxy is like. You can still see, there's still some clouds that are so thick, you can't see all the way through them. But you're now seeing more continuously what the disk of stars in the Milky Way looks like. And the bulge-like part of the center we call the bulge. And these two blotches toward me on the bottom, they're two smaller galaxies that are orbiting the Milky Way. They're called large and small imaginary cloud. So here's a schematic, like a little you are here diagram. In this schematic diagram, the sun's location is out there on the left. We're kind of out in the suburbs, you might say. When this figure was made, best distance is about 27 or 28,000 light years, probably closer to 27,000, a little bit off. Side to side where the stars are, that's like 100,000 light years. And the thickness of the disk is only about 1,000 light years. And then the disk itself is embedded in a larger thing that we call the halo. Sometimes when I use the word halo, people think of, the circle above a saint's head. But if you can imagine a medieval painting with just a glow around the head, that's more like what the halo is like. It's like a big puffy distribution of stars that is quite faint, that everything else rests inside. Here's now, this is not a picture of the Milky Way. We can't send a satellite way outside. We can look at the Andromeda galaxy, which is a counterpart, one of the nearest large galaxy to us, to give us an idea of what our Milky Way might look like from the outside. And the arrows are pointing different components. The bulge is in the center. The disk is going around it. The halo is hard to see, but it's puffy around it. And then there's a pointer going to what we call the interstellar medium. That's the gas that's in between the stars. It looks like some dark streaks here. And this is the kind of picture you would have seen in a textbook, and still can see in a textbook, decades ago. But over the last couple of decades, you begun to appreciate that a very important component of the galaxy is right at the center. The most massive black hole a galaxy has is sitting right at the center, and the bigger the galaxy is, the more massive the black hole is there. And I'll be showing you the evidence for that those things actually exist during this talk. So how do we know there's one there? Seems like a pretty big claim. In my class that I teach Michigan State, I always say I'm going to claim some outrageous things during the semester. And at any time, you can call me out and say, what's the evidence for that? Because I want them to learn why we can make claims and what supports it. So why can't I be confident about this? I'm going to take you on a journey now into the picture, into the Milky Way. So we're starting at this image. And if we zoom in on a square at the center, this is now toward the very center. And you can see this is a visible light image with a lot of dark patches. Those are gas clouds we're going to have to see through. So I'm going to be showing now some infrared images that help us zoom in. We're going to zoom in further, looking closer toward the center. Even infrared light, it can be hard to see through some of the gas clouds, but you can see that bright knot of stars at the center in yellow. So we're going to zoom in. With our zoom ins at the distance of the Milky Way center, that's about 250 light years across now. So we've zoomed in quite a bit. We're 28,000, 27,000. We're zooming to only, the picture is about 1,000 light years across. And then I also put in here a radio wave image. You can see there's something going on here in radio waves that you can't see in visible light. You can see filamentary structures, and the brightest stuff is still right toward the center. Okay, I'll take that away. And now we're going to zoom in to this picture. And this is several different observations put together from some of NASA's most famous missions. In the yellow light is an image from the Hubble Space Telescope. In the red is an image from the Spitzer Space Telescope, which is an infrared observing telescope. And then the blue is the Chandra X-ray Observatory. So you're seeing X-rays, infrared light, visible light all at once. There's a 50 light year scale bar over on the lower right. And this thing called Sagittarius A is, again, the thing that's right at the center of the galaxy. And it's got radio waves, visible light, infrared light, all that stuff coming from it. We're going to zoom in some more. Oh, forgot the students. There's also bonus. This is now zooming on the radio waves that are coming from the center. Now we're going to zoom in some more. Okay. So we've gotten now to only about 5 or 10 light years across. Okay. We've zoomed in, even in that zone, the nearest star to the Milky Way is about 4 light years away. So you can see in the center of the galaxy, it's a lot more crowded with stars. Okay. And we can still see radio waves from the center. There seems to be gas that's emitting radio waves that's swirling around. We're going to zoom in further. This is now an infrared picture. And that's just 1 light year across. And if we zoom in further, for the very center, what you're seeing here now, the colorful blobs, that's not actual color, that's just showing brightness of light. But these are the stars that are right at the center of the Milky Way. And those colorful lines are showing the orbits that people have observed. This is from the Galactic Center group at UCLA. Over a period of a few decades, they keep taking pictures of the center to see whether the stars have shifted their positions. And in fact, they're going around. And you can see they're all going around a certain spot. I will point at it for the people in the room. Right about here. And you can't see anything there. Okay. You can tell from the star's orbits, there's something quite massive that's tugging them around. And you can't actually see something at that location. We'll zoom in further and wait for the movie. Okay. Takes a little while to get started. There we go. Yeah, so you can see the year up in the corner. And why it took a multi-year project. It took a while to get all these orbits mapped out, but this is how it's done. They've now been looking at it for 3 decades. And the most impressive turns are, I'll start over. You can watch the star labeled S02 going from the top as it heads down. There's one star whipping around that center, another star whipping around the center. There's something that's very influential to the orbits of those things, and you can't see it. But you can use Newton's laws to figure out how massive the thing has to be there. And by combining these orbits to get the mass, they found whatever's there is 4 million times more massive than our sun. We're pretty sure that, well, there's even better evidence of it. Pretty sure there's a black hole there. And this discovery, there's a recent Nobel Prize awarded for this discovery. One of the 2 people who got the prize, Andrew Ghez at UCLA, I remember when she was a graduate student, just starting out on this project. Well, it paid off pretty well. Okay. This image is actually not from scientists. It's from the movie Interstellar. They actually had a consultant on this project, a famous black hole expert that helped. They wanted to get something as realistic looking as possible. In fact, they had more computer power than scientists had. So when scientists collaborated, they got a better visualization than they could do on their own computer. And I want to just clue you in as to what you're looking at here. This is actually an image or a simulated image of a black hole where the black hole's at the center. You can't see it, it's black. Black hole has gravity so strong that light can't escape. But the stuff orbiting is orbiting very quickly. It releases a lot of energy as it orbits. And there's where the glow comes from. And what this is a disk of stuff around the black hole. It doesn't look like a disk exactly in this image. But on the near side is the part of the disk where you don't have a distorted view. Okay, so you're looking at a disk like a hoop around there. There's the front side of the disk you can see. And you're also seeing the back side. How are you seeing the back side? Light from the back side of the disk, some of it's coming out and trying to go over the top of the black hole, but the gravity is so strong and curves space so much, it ends up directing that light towards you. So light can come from the top of the disk behind the black hole and come to you. It looks like it's coming from above. And also it can come from the bottom and come to you. So on the top is the backside top surface. On the bottom is the backside bottom surface. the black hole is distorting it. Okay, so that's, you know, if you're walking home tonight and you see some of that, stay away. Right. But this is, you know, how if you could observe everything, you know, that this is what it would look like. Okay. And this is an artist's conception, but you can see there's this drawing, there's stuff swirling around the black hole, and also a twisted jet going out. And when people simulate matter falling into a black hole, a lot of it goes in, but the energy release can cause a winding stream of matter to shoot out the axis. And in the first slide, that's what you're looking at. The stream of stuff coming out from very close to the center and extending out over the distance much larger than the galaxy itself. So this is all going on in a very small region of the center. And these streams go out to enormous distances. Here now, no, put the music back on. Got to make sure I don't echo. This is a zoom in to a galaxy called M87. You can see the jet coming out of the center now. This is invisible light from the Hubble Space Telescope. The blue is X-rays from the center. Or you continue zooming in. From now on, it's mostly radio telescopes. Okay, and using the most powerful arrangement of radio telescopes to date to see fine detail, they found the black hole at the center. Okay, so this is the Event Horizon Telescope. Is an ensemble of radio telescopes that are located all over the surface of the Earth, and they work together as if they were like a radio telescope with a dish the size of Earth. That's what they're using to get this level of detail. What you probably can't see is drawn on the center is an illustration of Neptune's orbit around the sun. Right. So if you were to take our solar system and put it at this location, it'd be inside that black hole. You can see this. There's just kind of an orange blur and a dark region at the center. Even with our most powerful telescope arrangements, we can't get a picture like the one they made for the movie. It's still a little blurry, but it's consistent with a disk similar to what you saw in that movie, the image made for the movie. And the size of the dark patch is determined by the mass of the black hole, and that's consistent with our other measurements of trying to measure star orbits around here. So over the last decade, the evidence that giant black holes like this actually exist is becoming stronger and stronger. And this was one of the signature achievements. Hasn't won a Nobel Prize yet. The same group a couple years later also made a similar image of the black hole at the center of our Milky Way. And so I don't have one of those in this talk, but you can look it up there. Okay, so I also had eruptions in the title. You know, what are they doing? So here's now our diagram of the galaxy, and I'm going to zoom out a bit. Okay, so this is the Andromeda Galaxy, Andromeda Galaxy, and I placed it at the center of these circles because we've learned that a lot of the gas associated with our galaxy is way outside of it. In fact, there's more hydrogen way outside of our galaxy, up in the halo, than there is making up stars in galaxy. How do we know it's there around galaxies like this? We look at some very distant things, beacons that are called quasars, and as their light passes through the gas around a galaxy, Some of that light's absorbed out. We can take it, look at the spectrum and detect, oh, there's actually something around that galaxy. I can measure what's out there. It's actually the gas supply for making stars in our galaxy. Here we're back to that galaxy called Hercules A. If we use an X-ray telescope, well, I guess maybe I don't have that one. What I wanted to point out about this one is there's jets coming out, but they don't go on forever, right? They look almost like you pointed a fire hose at a wall and got splashback. So even without seeing the gas around this one, you can tell there's something out there that these jets are pushing on. Okay. Right. I do have the X-ray image here. Here it is in purple. So even before this X-ray image was taken, you could tell there's something these jets were pushing on. Now the purple is showing you the X-rays from the hot gas that's around this galaxy. And so what we now have is a modern view of galaxies like this, is they're environments where there's a lot of gas feeding into the galaxy, allowing star formation to keep happening. But when gas feeds into the galaxy, you get explosions from stars or also feeding of that black hole that then erupts and controls the flow of gas back into the galaxy. So increasingly, we're looking at galaxies as if they were like ecosystems. And we're still trying to sort out exactly how all these things are connected. This is one example of how we do it. This is, I'm going to show you a little movie from a supercomputer simulation. And it's showing here gas temperature, and there's a 100,000 light year scale bar on the bottom. So in this particular simulation, that orange color is gas a bit hotter than 10 million degrees. Okay. But as it goes on, this gas is able to cool by radiating away some energy. And it's going to start feeding the setup at the center as an algorithm that's supposed to act like a black hole. So we'll start it up, and you can see jets coming out. But the jets we're shooting at this way, you're not seeing the jets. What you're seeing is gas that is cooling along that axis. You see the blue spots are consisting of lower temperature gas. So that's one freeze frame. And what I invite you to imagine going on here is similar to a thunderstorm. So I don't know how much, some of you may have studied thunderstorms at one point. But they come about because especially in the summer, the sun's heating up the Earth's surface, causing a lot of warm air to develop. That warm air rises, okay, it becomes buoyant. This process called convection. But as it rises higher and higher in the atmosphere, the pressure is going down and it cools off. Well, then if it cools off enough to hit the dew point, whatever moisture the air had in it condenses out into raindrops and they fall back down. Okay. That's what's happening in this simulation. The black hole's erupting. As it erupts, there's gas that's getting pulled up and it cools down as it rises. And as it cools, it's turning into something akin to raindrops. While it's in this extended arrangement, that's probably early in this process. But as I run the simulation further, you're going to see that stuff fall back in. So you keep running it, and it falls back into the galaxy. Now what you got is sort of looks like a mess. Right. Do we see things like that out in the real universe? Yes, we do. These are images from the Hubble Space Telescope, more like research type images. Okay. And they're showing ultraviolet light from new stars that are forming in gas clouds that appear to have been generated by this mechanism we call precipitation, akin to thunderstorms happening. And they're causing star formation spread out over distances of 100,000 light years in some cases. Sort of showing the connection between the eruption, new stars forming, falling back in. Again, like almost like the atmosphere of our Earth going through its cycle. This next image shows how this phenomenon called precipitation can also be self-regulating. I'll show, yeah, there's also, yeah, my colleague that made this added some nice music that goes with it. So cold gas, yeah, cold gases develop. Yeah, when it develops, it fuels the black hole, and you get these eruptions and more cold gas developing. And then that gradually gets used up. When it gets used up, you'll see the eruptions stop. Right about now. And then, if there's nothing to put energy in the gas, more of it will cool, fall back to the center, trigger more eruptions. Okay. And so this is how we're trying to work out the puzzle of how these galaxies behave over billions of years. Right. Okay. I'm managing my echo. See, the problem is I want to play some of the music, but then the microphone picks it up. So why do the eruptions matter? I'm now going to show you another fairly cinematic simulation. So the ones I just showed you are like trying to isolate and simplify the process so you can understand what's going on. This is an example of a state-of-the-art numerical simulation trying to put everything we know about into one bigger computer program. This one's called the illustrious simulation. This is a frame from the middle of it. I'm showing you what's coming in the movie. You can see on the bottom, it says time since the Big Bang, 6.9 billion years. Or maybe you can't see that. It's very, very, I'll keep you posted on time while the movie's playing. Might not be able to read that. But it shows how we model the formation of galaxies in the universe using a large computer simulation. Okay. The foreground, it's rotating. So it's just rotating so you can see the structure. Okay. Universe doesn't actually rotate like that. In this phase, what you're looking at is the matter that can't be seen at all. We call it dark matter. Gravity's causing it to collect into clumps. And as that matter collects into clumps, it's going to bring gas in with it. Okay. We're about 2 billion years in. And we hit to 3 billion years, the temperature map's going to change, and it's going to start showing you gas temperature. Okay. Where red will be hot and blue will be cold. And you'll see in the densest parts, the biggest, densest parts, you'll see red stuff, red hot gas. You also see flickering and eventually eruptions like that. That's in the simulation, the simulated black holes starting to erupt and push gas farther out, causing this kind of environmental effect. Okay. When the simulation gets to about 6, we're about 5 billion years after the Big Bang. We get to about 6, it's going to shift and show what's track new elements. Okay. When stars form in galaxies, they make elements through nuclear fusion that also get pushed out. And so right about now, not quite yet, maybe. We're still showing the gas temperature one. Yeah, now we've switched. Okay. So now you're seeing where element production has happened and how it's gotten spread into the surrounding regions. The green areas are the ones that have the most byproducts of stars. The purple ones, not so much. And then it's eventually going to switch back to the dark matter. So I just wanted to show this to kind of show a lot of the moving parts we have in and try to understand how galaxies evolve and change over time. You saw in the middle of that, some of this process has to do with the black holes erupting, not, yeah. Okay, so you might be wondering, what about our galaxy? Well, I'm reorienting you back to the oval picture of our Milky Way. And this is invisible light. But if you look for gamma rays, what you see is this. Okay? Gamma rays are they're light that is made by very energetic particles. And above the disk of the Milky Way, you see two bubble-shaped things. People do argue over whether the black hole did this or not, but it is reminiscent on a smaller scale of the eruptions we see in other galaxies. If the black hole did this, it means it was active maybe about 10 million years ago. Okay? It's not doing this now, but as we saw from some of the other movies, our simulations say these eruptions can be periodic. They're not always on. It's kind of bursting. And what you're seeing in this image looks like, I take this at face value, that this is probably some evidence of a previous eruption from the black hole at the center of our own galaxy. Okay. What I want to finish with are just going back to some of these visuals, because I really think they're beautiful. And we're going to go through a number of different wavelengths of light to look at what the Milky Way looks like. So here you're seeing the infrared image that shows you a view through the clouds. There we're back to the visible light image, okay, starlight. This is microwaves from little grains of dust that are strewn throughout the Milky Way galaxy. This is radio wave emission from dense clouds of molecules. These are the places in the galaxies where the stars form. And you can see they're concentrated quite close to the center, except for a few things that maybe look like bubbles that happen. This is atomic gas clouds out there in the Milky Way. This one is X-rays. This is hot gas. And what may catch your eye is that big bubble. Okay, that looks very much like the gamma ray thing. So again, this X-ray light is indicating some of it may be also from a previous eruption from the black hole of our Milky Way. And there's a gamma ray image. You can see very faintly. This is bubble evidence here and here. So that's the infrared. Yeah, this, I don't know. I love this image because it looks like Van Gogh. It's actually showing polarized microwaves, and the treatment of it, the kind of flow that you see, that's using a polarized light to try to map out how the magnetic fields are connected around the Milky Way. Who saw the aurora a month ago, roughly? Yes, only one person in the room. Yeah. So yeah, that's another magnetic field phenomenon. But the magnetic fields here are pervading our galaxy, and I don't know. I just love how it looks.
I just bought a T-shirt that glows in the dark. Yeah, the Aurora Borealis.
Oh, how appropriate is that?
Yeah.
Did anybody ever like make a mistake looking at your shirt? Like, oh.
No, I don't go out when it's dark enough,
Right,
you know,
yeah,
in
yeah,
this neighborhood.
All right. All right. Yeah, there's more microwaves. All right. And this is this last thing will turn into a movie. This is yeah, this map is showing atomic gas, but the animation tunes through how the gas is moving. So let's see if it starts up. Here we go. Okay. So soon you'll see some stuff that's moving toward us. That's over there. Okay. As we tune through, it shifts to gas that is neither moving toward or away, but this is still moving toward. Okay. And as we continue shifting through wavelengths that are either representing gas toward or away from us, you'll start seeing more on the other side of the galaxy. So this map is actually showing us how the gas is moving within our galaxy by looking at slices in the observation that tell us whether the gas is moving toward or away. But again, I show it largely because it's just beautiful to look at. So that's the end of my formal presentation. I invite you to ask questions, or I can go back to any one of the images that you wanted to look at. If you want to just feast your eyes again. Thank you for your time.
We have read the recent book by Panning on the web,
Okay.
the development of the Webb telescope.
Oh, right,
and
yes.
Some of the images over the last year.
That's right.
How is that impacting, because I know it's really deep into the infrared
Right.
side of things. Is that going to be able to cause these to be evolved even further in terms of your studies? Or is
So
it too soon to tell?
well, I think it is not too soon to tell. So yes, my closest collaborator is also my wife, also professor at Michigan State. Megan Donahue is her name. And she was recently awarded James Webb Space Telescope time to observe
Wow.
evidence
Wow.
for this phenomenon we call precipitation.
What they call oversupplied or over.
They say it's oversubscribed.
Right,
That's our technical
oversubscribed.
term. Yeah. Like, of course, it was going to be in high demand, right? And yeah, we feel honored and lucky to have gotten some precious time. And so some of our favorite examples of what looks like precipitation happening, what the Webb telescope is going to be able to do is give us some of the sharpest images yet. Okay. There's a number of tests we have in mind, and that's the technical part. But I think they will also be beautiful images. So the gas, there are certain wavelengths of infrared light that it emits. We have blurry images right now, okay? And there's only a few things we can see. And so the upgrade in how good the maps are going to be is going to be enormous with the Webb telescope. So we have 7 targets that were approved. And the data are coming. And next summer, we actually have collaborators in Paris who invited us to go there and work on it. So,
Wow.
so that's also a good thing. But yeah, these projects can be very international. But yes, we're thrilled the Webb is out there.
I mentioned a woman scientist named Hummel, or
Heidi Hamill?
Heidi Hamill, who
Yes.
got 100 hours.
Yes.
She was given 100 hours.
Right.
Now, she in turn then subbed that out. She didn't
Right.
take all 100 hours on it. But I'm going, that is amazing that
Yeah.
she was able.
Right.
Right,
She is
much
one of
time.
our most eminent planetary scientists. We're a very similar generation. We know Heidi. Yeah, in fact, yeah, I think my wife was on a meeting earlier today by Zoom where Heidi was probably also on that meeting.
Wow.
But yes, yeah, it's not that big a community. There's, yeah, when I say not that big, the number of active professional astronomers in the United States is a few thousand. So I've met a lot of them. And it's always fun to see what they're going to do next with these great tools.
They were saying too in the book is that there's so much data we've got already.
that they can work for years and
Right.
years on just the stuff we
Right.
have.
Well, yeah, and people, I want to make sure people listening on Zoom are hearing this here. What we're talking about is the tools that astronomers have available. There's so much data already, like why collect more? Well, a project that is just about to fire up is something called the Vera Rubin Observatory, previously called the Large Synoptic Survey Telescope. And it's going to be able to, every 4 days, take pictures that amount to the whole sky visible to it at that time of year. It's going to produce an enormous amount of data, okay? And part of the reason for going back and revisiting the sky every few days is to see what has changed. Supernova explosions at great distances, maybe stars where they're planet, and they have planets that are passing in front, causing a slight decrease in brightness. So again, as our tools get better, we have to come up with analysis methods that can take advantage of that. And so the progress of what sometimes is called big data and progress of modern astronomy have gone hand in hand. In fact, a lot of the pioneers of big data liked to collaborate with astronomers because many of the data sets that people want to do big data projects on are proprietary. They have to do with corporate secrets. Astronomy doesn't have corporate secrets. We just want help. And so people who are trying new things often want to collaborate with us because we got a lot of data and we need help. Yeah, so keeping up with it all is a challenge, but we like to rise to that occasion. There's a couple of questions over here. I have this one, that one. Yeah.
Well, I was following this in other places, but Joni Mitchell's song says, "We are stardust, we are golden."
Mhm.
And then a guitar player from Queen is also
Okay.
an astrophysicist.
Yes,
And he
right.
said that's true.
Yes.
But is it, when black holes or when this gas shoots out and they become stars and
Mhm.
planets, is that how we
Okay.
were part of this debris?
Yeah, so to back up, the question was about the sense in which we're stardust, and I showed a lot of chaotic things happening, and people willing to know, like, how much is that looking like our own past? The Milky Way, remember, is a very flattened disk. And I showed pictures saying a lot of the gas in our galaxy that's capable of forming stars is right down there on the disk. What that indicates to us is there hasn't been any super disruptive event that's happened in maybe the last 10 billion years. So sometimes galaxies collide with each other and turn into elliptical galaxies, but ours has lived a really relatively sedate life. When eruptions happen, they probably direct the energy away from the disk, right? So there may have been elements formed closer to the center of the galaxy. And if there was an eruption, those elements may have cascaded down on the rest of the disk, but the disk itself wasn't disrupted. Okay. It's the more massive galaxies that tend to be most disrupted by black holes.
Yeah.
Okay. So certainly around here, there have been supernova explosions that have disrupted things, not super recently. But the supernova, well, to kind of go back a couple steps, the elements such as oxygen that we rely on were made by fusion inside of stars. They have to get out somehow. Stars explode. If just one star explodes in the middle of nothing, there's no way for that to get recycled. Okay. In fact, the galaxy seems very vast, but people like us can only develop in that kind of vast ecosystem with the capability to recycle these explosions. Okay. So in our galaxy, it's likely the supernova part is the most important part of the ecosystem. But you go a little more massive and it's probably the black hole. And that is one of the topics that I'm working hardest on at the moment, is trying to understand the difference. Yeah. There's a question here.
I was wondering about AI.
Ah,
and
Okay.
Their usage already or future
um,
possible.
right. So the questions about AI. I have to say, right, AI is extremely fashionable in science right now. And in a way, what's hard to distinguish is in what project is it truly promising, and in what projects do people just want to try it out? And the thing about AI is it is great at pattern recognition and identifying things based on patterns. The mysterious part is you don't always know why it classified things as it did. So you feed it a bunch of pictures and you can put like with like, and you can stick labels on that, or you can train it by feeding a lot of images saying that's a cat, that's a dog, that's a cat, that's a dog, and then show it something and it can figure that out. But sometimes you don't know why it's making the decisions that it does. Yeah, one of my favorite examples from astronomy, failure examples is, I can't remember it exactly, but it had to do with evidence for how massive a galaxy might be, right? And so it was trained on a list, and then there was data associated with that list, and then it was given other data. And it got the classification all wrong because it learned from the first list, it depends on the order of the list. Like it was using that to do the classification. So it's just one of the many cautionary tales. But I think one of the pathways in the near term that I think is more promising is there are things we do to take a very noisy image and remove the distracting noise patterns, to remove some of the other things that are real but are not what we're looking at, right? And AI can be really good at doing that, can do a better job than we can. What I'd be worried about is allowing AI to make the scientific decisions. Pardon? The scientific decisions, to try to do the scientific interpretation. So you can say, AI, please remove all the distracting stars from this image. Like, yeah, done. Now let's look at the galaxy. Now remove all the spiral galaxies from this image. Okay, great. Now what are we looking at? You could do, give it those instructions. But when it comes time to interpret what you're now looking at, I still prefer human brains. But yeah, it's a great tool. But be careful. Other questions? Yeah.
I think it was in today's New York Times, there was a picture of a star. So is every sun a star, basically?
Yeah, basically.
Okay, so it said it was dying.
Okay.
And it had all this stuff around the edge flying around. And then it said, but it would take a long, long time for this to happen.
Right. Yeah.
But when it dies, it will be a black hole. Is that right?
I should have read the New York Times this morning.
No, I mean, I'm not knowledgeable enough to interpret what I was looking at,
So,
but I thought that's what it was saying. So then that makes me wonder, are you saying, are there lots of black holes? Are there lots of things dying? And
okay, so the question was about, prompted by a New York Times article, said, here's a dying star
right,
that we believe will end up being a black hole.
right.
And that is not a controversial statement in astronomy. We know most of the black holes we know about in our galaxy are maybe 5 to 60 times the mass of the sun. They're left over from star-like objects. Okay, how does that happen? I'm going to let's see. I'll get a little technical. Stars that are more massive than the sun, when they near the ends of their lives, they have fused elements up to iron. Right? But the problem with iron, if you're a nuclear physicist, is you can't fuse iron nuclei and get energy out of it. So it's like dead ash that piles up. When too much of it piles up, the gravity of that core collapses, and it can collapse either to make a neutron star, and the energy released blows off the outer layers. But there's a limit to how massive a neutron star you can make. The maximum mass is somewhere around 3 times the mass of the sun. If there's more stuff left over after the explosion, it's going to be a black hole. Now, we don't know enough yet to prove that that particular star is definitely going to be a black hole. A massive star that is going to end up leaving either a neutron star or a black hole. And it's one of these things that people argue about. Exactly what causes the black hole to be left. So yeah, the fact that a star could leave behind a black hole, not controversial at all. We found a bunch of such things in our galaxy. Whether that one will or not, well, time will tell, and we might not be here to answer that question.
So there is a one massive black hole and then smaller ones?
That's right.
Is that?
Yeah, so the one that's at the very center had a different origin. We don't know exactly what its origin was. It's probably been something like it is now since very early in the history of the Milky Way. But exactly how it got there is another cutting edge research question. It wasn't just a star. Any other questions? Yeah.
How is gas contained if there's nothing to contain?
The answer is gravity. So put it this way: if we think of Earth, right? We have the atmosphere. It has a bottom. The top end, the Earth's atmosphere is just a thin layer. Okay, and in fact, the thinness has to do with how does its temperature compare with the temperature it would need to have in order for it just to flow out into space. Luckily, it's colder than that. Technically, the Earth doesn't retain hydrogen because the hydrogen is still moving too fast and it gradually escapes, but you're left over with our atmosphere, which has no top to the container. In these galaxies, I showed you some pictures where the gas seems very puffy. And that's because the temperature of the gas is almost enough for it to escape, but not quite. And so you end up with a very puffy atmosphere around a galaxy compared to the Earth's atmosphere. Okay. So this is another. I have a website called Galactic Atmospheres, which has pictures and some scientific explanations of what those atmospheres are like. But yeah, that was a good question. Just glad you're thinking about that.
So it's really cold out there is the answer.
Ooh, that's an interesting question. Yeah, I have to choose my words carefully when we talk about heat and cold. And when we're talking about this with my general education students, they say, would you rather put your arm in an oven at 400 degrees or a pot of boiling water? Okay. And I hope people choose the oven. The pot of boiling water is colder in temperature, but there's a lot more molecules there and they transfer their heat a lot more quickly. So your perception is that's much hotter. Okay. If you go out into space, the gas particles might be moving around quickly, but they're not hitting you very often. So they don't transfer, it wouldn't feel hot necessarily. Yeah, again, we want to put you out there without a spacesuit. But perception of heat and cold depends on is my body losing energy or gaining it? And if you're out there in space, you're radiating energy away, and you might not be gaining much back from the particles that are hitting. Yes.
Now, old Star Trek.
Old Star Trek.
With the tractor beams, they
right.
had these old. They didn't call them black holes or whatever, but it sucked everything in.
Yep.
And it doesn't come out.
Yep.
Why doesn't it suck the whole universe in and you can't get out?
Okay. I'm glad you brought up old Star Trek. I'll tell it this pretty straight. Again, my wife, she should have been here.
The first group.
I'll just-
OG.
So way back when we used to go on long car trips with our kids, when they're bored, they wanted a story, and my wife would just tell them the plots of old Star Trek episodes. That was one of the ways to pass the time.
Yeah.
So yes, what's called a tractor beam in science fiction is useful for the plot. I don't know how you'd actually make a tractor beam.
Okay.
But people, black holes in popular culture movies have this reputation of being able to suck everything in.
Yeah.
But if I were to wave a magic wand and turn the sun into a black hole, its gravitational pull on Earth wouldn't change. Okay. It just matters, all the black holes are doing is exerting gravity. If you're far from it, there's no sucking.
Yeah.
You just keep going around. The only place around a black hole where gravity acts different from Newton's laws is very close to the center. Okay. Then the orbit spirals in. Okay. But there's still no sucking, right? And I kid my class, we like to say, the slogan is black holes don't suck. It's gravity. And so we're really rather safe. It's actually hard to fall into a black hole in the sense of, they're not, the way it's made is you pack so much matter into such a small space, the gravity is really strong. So if you get close, there's trouble, but it's not very big in physical size. Okay. Right. And so if you have to try hard to fall into it. You have to have very good aim. So it's very unlikely that we'll be doomed by a black hole around here. So in the end, it's gravity.
Okay.
Yeah. Everybody's sleeping better tonight. Question.
And when are we going to understand gravity?
Well, it depends on how demanding you are. Right? Isaac Newton, were he here today?
It goes back a long ways, but I actually edited a book that a friend of my husband's wrote on his theory of gravity, which was basically that we can't understand it because we only understand material things. And it is immaterial. And I give people the example that a fish can't tell you anything about water. It just is.
Right.
Yeah.
So,
we know it has effects on things, but because it appears to be immaterial, you can't photograph it, but you can see what it's doing to the other things that are part of it.
No, so this is an interesting philosophy of science question, because really, science likes to get a lot of answers. But it's like you can all be the 3-year-old who keeps saying why. Right. And I can't stop the whys from coming. Why this one? What I can say is there are numerous ways in which Newton's laws and the successor, Einstein's theory of general relativity, have been tested. There are aspects of gravity that we can model very well, we can predict very well. Can we explain why it happens that way? That's there's some level at which, that just becomes the next question. And, I can talk about all the evidence for the Big Bang, and they say, well, why did it happen? I'm like, I can't answer that one. We can describe a lot about it. And again, with my class, I say, you're doing science if you're trying to explain observed features of the world around us, relying on natural explanations. But there's always another question you can ask about it. And that's part of what keeps us going.
And it's not necessary to know all of these things in order to get on with your life.
Yeah, I don't know my wife's coming again, and she's really good here, and she should get credit. I know she drove her chemistry teacher crazy. She was destined to be, astronomer or physicist, because when she wanted to know why there's charge, electric charge, and she thought they were hiding stuff. I think, why don't you answer me? Well, yeah, probably very. I don't know if the teacher thought this is great or very annoying, but yeah, she thought there must have been some kind of conspiracy to hide the truth. Will that be it?
Thank you so much.
Thank you.
Our next presentation is going to be on January 7th, titled Cold Cases in Universities, presented by Allison Rojek. She's a professor here that works in the criminal justice department and former teacher of mine, very good teacher. And it's a collab with MSU PD as well. Sergeant and Lieutenant Larry Rothman will be here as well presenting with her. So looking forward to it, January 7th. Thank you.
Very good. I